Before I start, I want to say thanks. I've never before had such a resounding and unanimous critique of one of my videos. Now I know they're not all great, but to hear all you guys say, "Oh, it's terrible, you totally messed that one up," algebra mistakes and blah blah blah. I honestly appreciate hearing that from you guys, and thank you. Thanks for saying that. Now, I appreciate the fact that you didn't say, "You're a moron, you're a horrible teacher, I feel sorry for your kids because you're surely a terrible parent too." The personal kind of insults. But to tell me, "Hey, Dress, this video kind of sucked," that's all right. I honestly really appreciate that. So I'm going to do over, right? Just like in grade school, do over. And so here we go, my second take on second order forced differential equations. So what are these all about? Let's take a look. There we go. All right, full screen. So the second order differential equation with forcing. So this thing here, I'll underline this here, is called our forcing function. Why is it called forcing? Because we'll do that. I'll show you that in another video. Video called Why Forcing. All right. And I'll make that video as soon as I'm done with this one. But it's kind of cool. And I like calling it, rather than something else, a non-homogeneous or whatever. I like to call it a forcing function because that's physically, to me, the knuckle-skinning mechanical engineer. That's really what it is. So how do we solve these problems that are not nice and equal to zero? What is the theme of this course? What is the theme of every math course from here on out? Make the problem look like one you know how to do. So what do? We say, all right, fine. I'm going to solve this one instead. Solve easier problem. And my easier problem is going to be y double prime minus y prime minus 2y equals 0. Right? So now this is homogeneous. And I'm going to say this is the complementary homogeneous problem. Right? It's complementary because, it's related to this problem in that the derivatives are all the same. The differential operator is the same. But I neglected the forcing function, so it kind of is the complementary problem to this one. All right. We know by now that after some toil, we will get this r squared minus r minus 2 equals 0. And from that, hopefully by now, second semester calculus, you can say that r will equal, what will it equal? 2. So it's 2, and r equals -1. So we can get two solutions out of this. Our two solutions are y1 equals e to the 2x, and then my other solution is, let's see, negative e to the negative 1x, or just e to the negative x. All right. What does it mean that these two are solutions, and why do we add them up? This matters, so I want to take just a moment to go through this. The reason we add these two things together is because, I forgot one important detail. So y1 equals c1 e to the 2x, and y2 equals c2 e to the 2x. Because I could multiply this by any constant and the derivatives would still work out. What do I mean? The derivatives would still work out. What I mean by that is if we took our first solution, right, y1, so it's c1 e to the 2x, and I took the second derivative of that. Why the second derivative? Because that's what my differential equation calls for. And that's what my complementary equation calls for. Y double prime minus c1 e to the 2x prime, right? Because that's what it calls for. And then minus 2 times C1e to the 2x, right? And what would that equal? Well, let's see. This would be, every time I take a derivative, a 2 comes out, so this becomes 4 times C1 e to the 2x, minus, take a derivative here, just one derivative, so it's 2 C1 e to the 2x, minus 2 C1 e to the 2x, 4 C1 e to the 2x, minus 2 C1 e to the 2x, minus 2 C, well, that equals 0, right? That's nice, because that's what I was going for in the first place. Likewise, if I take C2 e to the negative x minus, double prime, minus C2 e to the negative x single prime minus 2 times C2 e to the negative x, just no derivatives, just the function itself. What does this equal? Let's see, the negative comes out twice, that stays positive, so positive C2 minus a C2 will give me, let's see, minus positive minus, that gives me minus positive, this becomes positive, so that becomes 2 of them, 2 C2s, minus 2 C2s. Oh, how about that? That equals 0 too. Wow, all right. Now, if these two things together, or these two things separately, each equals 0, I know that C1 e to the 2x plus C2 e to the negative x double prime, minus this whole thing again, prime, minus 2 times this whole thing. Well, what's that going to equal? Well, this equals 0 by itself, this equals 0 by itself. So if you were to go through and do this and crank it all out, you'd wind up looking exactly like these two separately. Well, that's going to equal 0 too, right? That's this really important concept of linear superposition. So I'm going to write that one more time. This is called linear superposition. That's one of those math words that I don't really understand. But to superpose things, we put them on top of each other, right? Add them. And linearly, because we can add any constant multiple of these things, a linear constant multiple, and it still works. All right, so what does that mean? That means that our YC, I'll tell you what that is in a second, equals, well, whatever our Y1 plus our Y2 equaled. And what did those equal? It equaled E to C1 e to the 2x minus or plus C2 e to the negative x. Okay, I'm in my basement right now, and the furnace is just about to start. So I got to quick turn off the furnace, and then I'll be right back. Okay, so my furnace turned off. Now my wife and son can freeze upstairs, and at least we can do calculus down here. All right, linear superposition leads us to this solution here. This solution, however, is not the solution I want. It's y sub c, which is the complementary solution. All right, why is it called complementary? Because it solves the complementary problem. I could take this function here, this function, c1 e to the 2x plus c2 e to the negative x, and I could stick it into here, y double prime minus y prime minus y. So I'm not trying to solve for y here, I'm trying to solve for a function. I plug this function into this differential equation, and it works. It gives me the 0 that I'm after. All right, complementary solution. The problem is that's not what I was trying to get. That was not the problem I was given. And by the way, I pulled this problem right out of the Thomas chapter 17. I still need a different solution. Let's see, I still I still need a solution. I still need a function y so that y double prime minus y prime, that should be 2 primes there, minus y prime minus 2y. I don't want it to equal 0. I want it to equal 20 times the cosine of x. All right, this is the problem I'm after. So this is what I need to pursue. All right, well, let's make a guess. Right. My guess is that since I need to take derivatives, a double derivative here, a second derivative, a first derivative, and then the function itself, and this all has to add up to be a cosine. Well, how do I get that? It's got to have some sines, it's got to have some cosines, probably. So I'm going to guess that y equals some number of sines plus some some number of cosines, and that when I take the derivative and the second derivative and blah 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 blah, that's going to give me this 20 cosine x that I'm after. All right, or in other words, I want it to work out such that a sine of x plus, I'm having trouble with my pluses, plus b cosine of x, this thing double prime, minus a sine of x plus b cosine of x prime minus 2 times, boy, this is a hassle, a sine of x plus b cosine of x, just regular. I want all this to add up so that it turns out to be 20 cosine of x. Right? That's what I want to happen. But do you agree with me that this is a real pain to write out? I mean, I hate to make you sit and listen to me write this out the whole time. So maybe we need some shorthand. We need some shorthand to write this thing. And what I'm going to do is to say L, right, this is a differential operator, acting on some function y really equals d squared dx of y, the second derivative of y, right? That's my input, and this is what happens to it, minus d dx, I'm getting down towards the bottom of the page where it doesn't work very well, of y minus 2 times the function, right? It used to be that a function, right, you plug a variable in and you do some things to the variable. You plug a 5 in, you plug a 7 in, whatever. Now we're plugging in a whole function, so this is a differential operator. That operator says I take the second derivative, from that I subtract the first derivative, and from that I subtract 2 times the function itself. So I need L of this to equal 20 cosine of x. All right, so that's going to make life a little easier on us in a little bit. Next, so I want L of a sine of x plus b cosine of x to equal 20 cosine of x. Well, how do I make that happen? I know that my L includes a second derivative, so my y particular, this P stands for, y double prime is going to equal, let's see, a take the sine, derivative of that as cosine, take the derivative of that as negative sine, so that becomes negative a sine of x. And I take the second derivative of this, cosine becomes negative sine becomes negative cosine, so that becomes minus b cosine of x. That's my y double prime. And let's see, my single prime, y single prime particular, is, let's see, I take the derivative of this, that just goes to a cosine. Right? Stop me if I make an algebra mistake here. And then a single derivative of this, cosine goes to negative sine, so it's negative b sine of x. Right? And then y, of course, is just the regular thing. So now my operator acting on this whole thing, remember, is the second derivative. So it's negative a sine of x minus b cosine of x minus, right, my single derivative, which is a cosine of x minus a cosine of x minus b sine of x minus, go down here, minus 2 times my original function, my original guess, which is a sine of x plus b cosine of x. All right. So this is now my, this has to equal, holy camoli, 20 cosine of x. All right, we can do a little bit of algebra here. And let's combine, well, this negative sign distributes here, so we got to keep that in mind. Let's do the a and the signs. So this is negative a sine, a signs, minus 2 more a signs, and that's it. Okay, so it's negative 3, right, I think it's negative 3, negative 3 a sine of x. Okay, let's do b signs. Minus, okay, minus a minus, so it's a plus a b. Yeah, that's it, that's only b sine plus b sine of x. And then let's do a cosines. So then minus an a cosine, that's it, just one of those. Minus a cosine of x, and then finally b cosine. So minus a b cosine plus a b cosine. Is that right? Minus a b cosine plus a b cosine, and then minus 2. Oh no, that's a b sine. So minus a b cosine minus 2 more b cosine. So it's minus 3 b cosines. Has to equal 20 cos x. All right. Well, I can combine my signs, so I know that minus 3a plus b. I don't know, my handwriting is getting so bad. These are all my signs. And then the cosines is minus, I'm gonna add these actually, plus a negative a minus a 3b minus a plus 3b. Right, yeah, that's good. Times cosine of x. So minus, plus minus, oh no, that's got to be minus still there. Right. I think if I distribute my negative signs correctly, yeah, because that's minus a and minus 3b, yeah, equals 20 cos x. All right, well, now here's where we can do this coefficient matching thing. I don't have any signs. I'm trying to finish up with no signs at all. So this negative 3a plus b has to equal 0. Well, that means that b equals 3a. And I know that negative a minus 3b, I'm going to wind up with 20 cosines. So negative a minus 3 times b has got to equal 20. So that, and I can plug that b in there so that I combine these two guys here. Now this is just algebra, right? I combine those two together with substitution. So minus a minus 9, 3 times, oh no, b is, yeah, 3a. So that becomes minus 3 times 3a equals 20. So that means that minus a minus 9a, so it's minus 10a equals 20. Right, so a equals minus 2. And that gets a dotted box because that's pretty important. And then if a equals negative 2, then b must equal negative 6. And that gets a dotted box. Right, I know I kind of crammed this in here. I may not be, I'm saying organize your work better than this, and this is what I do. So do as I say, not as I do. And now that I know my a and b coefficients, I can put this all together and say that my y particular, solution, remember it was a sine of x, so it equals negative 2 times the sine of x, and then minus 6 times the cosine of x. Right, so if I plug this into my differential operator, sure enough, I get 20 cosine x. And you can try that, just to be sure. It'll work. So this is my particular solution, but I have a little problem here. This leaves me no flexibility, right? Because if I put L of my particular solution, negative 2 sine of x minus 6 cosine of x, right? That will equal 20 cosine of x, right? What is L? Let's revisit what L was. Let's see back here, I think we did it. Yeah, L is the second derivative minus the first derivative minus 2 times the original function, which is what we've been doing this whole time. But we have a little issue. We'll put the issue in red. That little guy there. So only these coefficients right lead to this function. Right? Those are the only ones that work. I have no flexibility. Right? I have no flexibility to meet my what? To meet my what? My initial conditions. Right? That's bad. Right? That's problem number one. Problem number two, I don't have any constants of integration. Right, so that's bad too. Right, so what do I do about this? Well, here's what we do. We did all that work earlier to find the solution to the particular solution, or the complementary. So I know that from way back when, L is the differential operator, like the second derivative minus the first derivative minus 2 times whatever. L of y1, well, that equals 0 for sure. Right? L of y2, right? That equals 0 for sure. And L of y particular, for that kind of funny little ending, I got 20 cosine of x. So what do? I add them up, right? That's what calculus is all about, adding stuff up. Well, I know so that L of y1 plus y2 plus y particular is going to equal 0 plus 20 cosine x. So that's going to equal 20 cosine x. Well, what were those? So L of y1, I believe, was c1 e to the 2x plus c2 e to the negative x plus, and let's see, what were those, negative 2 and negative 6? Negative 2 and negative 6, all right? So negative 2 sine of x minus 6 cosine of x, all that will equal 20 cosine of x. So that means my y, right, is c1 e to the 2x plus c2 e to the negative x minus 2 sine of x minus 6 cosine of x. Right? So that's it. That's my final solution. That took a long time to get one solution. That's why I only assigned 3, 4 of these things, maybe 5. So that's it. Okay, hopefully you understand that. But the problem is, right, and there's always problems. That's the problem with having an engineer as an instructor. One of the many problems is that that's just for cosines, right? And I made this, I made a guess here. If I've got a cosine or a sine, then it's probably going to have some sines and cosines in it. How do we make other more intelligent guesses? Well, we turn to someone smarter than us. That'd be Thomas. And, I'm in the wrong class here. We got to go to class, Calc 2, lectures, chapter 17.2. Why particular guesses? Look at that. So we have a nice little table to work with. And if I can make that a little bigger, as big as I can do it, we'll talk about this briefly. Right. A double prime plus B prime plus CY, that blah, 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 equals this G of X. This is the forcing function. Let's label that forcing function. So this thing here is my forcing function. All right. So we already did one like this. If it's got sine of kx and cosine of kx, like that. Now it's important that these two things match. The k's match here. I'll make a note of that. K's match. Right. And ki is not a root of the auxiliary equation. That's really important. That leads to resonance, which I'll talk about later. Hopefully we can get to that, because resonance is what really becomes cool. So it's kx. Well, I'm going to guess, we guessed A cosine x and B sine x or something like that. But you need a couple constants here that you can tweak those and get the derivatives to work out. Now, what if it's an exponential, right? If our forcing function over here is an exponential, R is not a root of the original equation, right? The complementary equation, they call it here auxiliary equation. So r didn't show up in our complementary solution, then we can just use a e to the rx as our as the guess. They call it a trial function. I call it, let's cross that out here. Then include this expression in the guess. I like to call it a guess because that's really what we're doing. So include a e to the rx, right? And just like we did in 17.1, if r already shows up, right? If it's a single root, r showed up in one of our solutions for the complementary solution, then we'll just use ax e to the rx, x, right? If r is a double root, so r showed up twice, we already had to use ax e to the rx, well then we have to use ax squared e to the rx, right? This will make more sense when you try these, but we've already used ax e to the rx, so then we've got to take it a step further, say ax squared e to the rx. Right, and finally, it gets pretty easy if we have a polynomial on one end, we just have to make sure that we have a polynomial here. Same deal. You know, we always have to be kind of thinking about it's x squared plus ex plus f. If 0 is not a root of the original thing, and then you know, keep increasing the power of x. Right. If you have questions about ask this, because it's a long, drawn-out kind of explanation to show examples. But every time I have already used my root, I have to use another value of x. So if I used r twice, I have to add 2 more values of x. Same deal here. If I didn't use it, I can just use some polynomial that looks like this. If I already used 0 as a root, then I have to add another power of x to get this. And if I used it one more time, like this. Okay, so I only did one example. I didn't do an example with E, and I didn't do an example with this because it would take forever. And these are long. I assigned a few of them. I encourage you to work through them because these second-order differential equations really show up a lot in the scientific world. And I hope you guys are familiar with these. At least until you take DiffQs, and you'll really beat them to death. All right, that's it. Thanks, guys, for listening. I will see you soon.